Let's wait just one more minute. Okay. Okay, are you ready, Kenta?
Yes.
Yeah. Okay. Yeah, let me welcome back, everybody. And yeah, let me introduce to Kenta Hotokezaka from the University of Tokyo. This is the last talk for the day. So go ahead, Kenta.
Thank you for inviting me this workshop. So the first day, Udi gave some open discussion in open questions in neutron star merger. So I think I should tell some different questions so that I choose Kilonova and R process. And I will talk about something like this. So these are the questions that I will discuss. So maybe like Uday's talk, you can jump in the middle of my talk and then give some answer or raise a discussion, anything will be welcome. So I will talk about those questions. I will give you some partial answer from me, but this will not be like full answer. So let's begin with this first question. So the first question, of course, what is the composition of mergers or merger ejecta, or what really the mergers produce, which elements are really produced? And then this is the solar abundance. So from the first peak, second peak, lanthanoid, and third peak, we always talk about this, but how much do we understand that? What we can tell about the composition from the merger ejecta from the observation? That's the question what I would like to ask. For example, if you look at the outcomes of merger simulations, I picked up few different results from different groups. So in a different conditions, for example, dynamical ejecta gives some certain abundance pattern, and then post-merger ejecta also gives some abundance, which of course gives you the progenitors that if you have hypermassive neutron star or black holes. So depending on the progenitor, we have different kind of composition. So we would like to really know what's the composition from the observations, and then we can start to say about progenitor of the neutron star mergers. So what's the current situation? So what we can really say from the observation? So observationally, what the most robust thing is, of course, the energy conservation. So the strongest constraint coming from the light curve. So here I show you the luminosity. So this is the bolometric luminosity of GW17 kilonova, and different curves showing the using different heating rate with certain given abundance. So for example, this purple one here, magenta one, is just I took the nuclei from the mass number of 72 to 85, which is the first peak. So around here. And then beyond the first, so then the green one here is including from the first peak to the third peak. And then the middle one here is something around the second peak. And the finally gray one is just beyond the first peak. And the striking feature here, the most robust thing, what I can tell you is if you just use first peak, even though you can explain the early light curve, the most of the time you can explain the light curve, but there are lower limit that observed by Spitzer telescope. So definitely, if you use only the first peak, you cannot explain the late time observations. You don't have enough heat. So there's just, we don't have radioactivity around this time scale. So from what we observed, we can be sure that the first peak only cannot explain the observation. That's currently, we can robustly say from just energy conservation. So related question is, what is actually the main energy source? This is another important question. So maybe alpha decay, maybe beta decay, maybe gamma rays from decay, maybe fission. So currently there are different scenarios are proposed, but beta decay and gamma rays are quite robust because we know the experimental data from nuclear experiments, like what is the beta decay lifetime and what is the energy goes to the beta electron, the neutron, and the gamma rays. Those are all measured. And so beta decay heating is, I would say, standard. But depending on the nuclear models that you use, you get alpha decay and fission as well. So for example, the light curve just here I show you is just the model where we use beta decay. So beta and the gamma are just the source of the energy. But there are some there are some nuclear mass models that predict a huge amount of alpha decay, for example, this case. So this is again, blue one is total heating rate, and the purple here is the beta decay contribution. So even though at early times, the beta decay dominates your heat, but later time, let's say 10 days or maybe even around a few days after the merger, your heating rate is dominated by the alpha decay. So in that case, the kilonova is powered by alpha decay. And also there is some suggestion, for example, californium has some interesting time scale. So maybe late time we may be able to see the fission from californium if there are enough amount of californium, but that also depends on the nuclear mass model, how much californium you will get from the merger ejecta. So those are another interesting question. Okay, so I want to proceed something a little bit more. So now I want to go into the question more like what's the spectra and what the radiation transfer processes. So many of you have seen this figure that this is the observed spectrum from 1.5 days to 4.5 days. And then this paper, Watson et al. 19 showed that this is they claim that this is the absorption of strontium, so singly ionized strontium. And then initially you see absorption feature, which is blue shifted. And then later you see still blue shifted absorption plus red shift, not red shifted, plus some emission line. This is looks like P Cygni profile. So it's kind of convincing this maybe P Cygni profile of some line, but is it really the strontium? That is my open question. So because there are some problems of interpretation of strontium, because in their analysis, they have to change the strontium mass with time, and more strontium is needed at the first epoch, and then less strontium is required for this later. And also, if you try to model this, the total mass is actually really small to produce the total luminosity. So it's some inconsistency going on. And also this paper from Albino Perego, he suggested it may be not strontium, but helium one. So this is an interesting question. And I would like to give some partial answer from my answer. So what I'm talking about is, so for strontium, strontium has a line around 10,000 angstrom, which actually the line here. So this is absorption line from doublet D state to doublet p state. This is the absorption line, and this, because this is a forbidden state, so there are some population around here. And also helium-1 has strong absorption line around very similar wavelengths, which is 10,830 angstrom, which is quite famous absorption line. But this is also famous that this absorption cannot exist under the condition of local thermodynamic equilibrium, because this is absorption from this triplet S state to triplet P state. And this triplet S state is actually 20 electron volt above the ground level. So 20 electron volt is much higher than the temperature of this Kilonova photosphere. So those Kilonova temperatures are like 5,000 Kelvin and 3,000 Kelvin, but 20 electron volt is much, much higher. So there is no chance to excite this. So that you have to go beyond local thermodynamic equilibrium. That's a tricky part. So let's discuss this a little bit more. So let me skip this slide. So I want to show you some order of magnitude estimate, what can be possible. So the optical depths of the line, in order to produce absorption line in a spectrum, you have to have optical depths to be more than unity. So the line optical depths you can estimate like with this formula. This is called Sobolev optical depth. So some physics constant times the time after the merger here, and then density, number density of the level that is responsible for the absorption line, and wavelengths and oscillator strength. And it can be written like this: at 1 day and 1 micron, it's 10,000 angstrom, is written like this. And we know what is the oscillator strength of this helium-1 line is about 0.5, and oscillator strength of strontium line is about 0.09. And requiring, say, 3.5 days, the optical depth is more than unity, we have this estimate. So the helium-1 triplet S state must be larger than 2 per cubic centimeter, and the strontium doublet D state should be larger than 14 per cubic centimeter. So if we can satisfy this condition, you may be able to explain the absorption line by these elements. So let's remind you what's the ejecta condition. If you have, say, in total 5% of the solar mass, then you assume some density distribution around 0.2 C, which is around the photosphere. The total atomic number density is about 5 times 10 to the 6 per cubic centimeter. And let's assume both helium and strontium are 1% in terms of the abundance, then the total atomic number density is 5 times 10 to the 4. So the question is, how many will be in this state, helium-1, triplet S, and then strontium-2 and doublet D? So first, I would like to show you what's happened in LTE and why I said it's non-LTE is required. So the helium-1 case, because the temperature is only 3,000 Kelvin around the photosphere, so that your ionization state is all helium-1. So helium-1 abundance is unity. And then for strontium, you can still ionize strontium. So the strontium-2 is the most abundance. And then you can also estimate what the level population should be. So helium-1 triplet 3 states, you have to have 20 electron volt. So there is no chance. So that you get this Boltzmann factor of 10 to the minus 30. So it's practically 0. And for strontium-2, you don't have to have such large energy difference. So you don't need large excitation energy. So the abundance is 5 times 10 to the minus 3. And put those numbers you get the, okay, in LTE condition, the number density of helium is 0. And then number density of strontium-2 is about 200 per cubic centimeter. And then that is much more than enough compared to the, to explain the strontium-2 line. So in LTE condition, we can say the strontium line should be very, very strong, and the helium-1 line is quite negligible. So, but I would like to tell you, it's not necessarily correct, and the non-LTE effect is quite important to analyze this kind of thing. And to get non-LTE, to get an idea how non-LTE is important, we need what the non-thermal electron is doing. So we know that kilonova is powered by radioactivity, so that by definition, you have radioactive electrons there. So in the ejector, there are so many radioactive electrons going on. So they ionize and they try to deviate the ionization state to a higher ionization state. So here is the, the spectrum of non-thermal electron. So if you inject electron at, say, 300 keV by beta decay, so you have this kind of electron spectrum. So the first injection point is here, and then they lose energy through the ionization. And then you see some increase because there are secondaries. And so secondary contribution enhance the electron flux. And also you can see this kind of peaks, some peaks here. Those are not the errors, but they are OJ electrons. So that sometimes electron ionize inner shell and then you get OJ. So this is the OJ contribution. And in the end, your electron spectrum going down at low energy because of the Coulomb collision cool down this non-thermal electron. Okay, so with this electron flux, I can calculate what is the ionization efficiency of the radioactive electrons. So let's do this exercise. So ionization is no longer determined by Saha equilibrium, but now I have to solve the ionization balance. Ionization is roughly, ionization rate is equal to recombination rate, which I solve this kind of thing. So this is a very rough estimate. So ionization rate is the heating rate divided by the work per ion pair, which is how much energy you need to get the one pair of ion. So this is work per ion pair, depends on the type of ion and then electron flux shape. So we know the heating rate here is 0.2 electron volt per second per ion at 3.5 days, and work per ion pair is about 300 electron volt for strontium and then 600 electron volt for helium-1, and times density. This is ionization rate. So recombination rate is, of course, the recombination coefficient times electron density and then 1 times higher ionization state density here. So if you do this ionization balance, what you get is helium-1 is actually 10 to the minus 2, and there are helium-2 50%, helium-3 50% around the photosphere. And then strontium-2 is now suppressed by this radioactivity. So what you're mostly dominated by strontium-3. So now then let's get level population. So level population of strontium-2 is, again, it's similar to LTE. It's 5 times 10 to the minus 3. And the helium-1 state is completely changed because what you have to do is helium-1 in triplet S state is formed through the recombination. So you recombine from helium-2 and then produce some excited state of helium-1. And then because there are ground state is singlet state, and then now metastable state is triplet state. So 75% goes to the triplet state, metastable state, and then 25% will go to the ground state. So that therefore this production rate of helium is recombination from helium-2 times 50%, and divided by occasionally some helium metastable state collide the electrons and then depopulate it. So this is estimated by like this. So helium-1 population must be 10 to the minus 4 from this calculation. So after taking into account all this, what you get is about helium-1 triplet S state is about 10 per cubic centimeter, and strontium-2 double D state is 10 per cubic centimeter as well. So both number densities are comparable. So this means around 3.5 days optical depth can be more than unity for both strontium and helium-1 if there are same comparable abundance. So we did some calculation, numerical calculation as well. So the left-hand side is, oh, it's terrible. So sorry. So the left-hand side is strontium case and right-hand side is helium-1 case. So both actually can explain this snapshot. But if you consider time evolution of the spectrum shape, we feel like helium-1 may be more consistent with the observed data. And also in terms of abundance, the strontium-2, we need like 1% in terms of the mass, and the helium-1, we need 10 to the minus 3, 0.1% in terms of mass. Okay, so maybe some of you think I'm crazy that sometimes I'm asked that, okay, neutron star major wouldn't have helium, but actually they have helium. So let's go back to the abundance slide here. Okay, so here, these three figures show the abundance pattern from hydrogen to very heavy elements. And you can see there are actually some cases you see a lot of helium production. I mean, heliums are left over from the nucleosynthesis. So actually, in some cases, helium is the most abundant element in the Kilonova ejecta. So it's not so crazy to think about actually what we see in this spectrum is the helium 10,800 angstrom line. So that is my, so maybe you have some objections, but this is so far my conclusion. And can I proceed or any questions so far? Is that okay?
Yes, feel free to jump in. Don't need to raise hands. Let's see how the discussion goes.
Okay, so let's proceed. So of course, another question is, okay, so it was a little bit of details, but let's come back to the open questions. So how much angular dependence is another interesting topic that we have actually, from many years ago, we have expected that maybe equatorial plane, we have low electron fraction ejecta, but while the polar direction, we have high YE, so that maybe there is some viewing angle dependence of the kilonova. That's we will get some answer from the observation in the future gravitational wave observations. That's of course an open question. It's quite short. Okay, so another interesting question that's also Udi was telling us in few days ago, what massive neutrons are really. So if we have stable massive neutron star as a remnant, what really they do? So, and then why we haven't seen them? That's an interesting question. So if we have low enough mass binary mirages, then they produce this kind of stable neutron star, which release its rotational energy. Oh, okay. So there is a question.
Yes, we have a question in the chat.
I got a question from the chat. Okay.
Yeah, from Philip Chang.
What I understand, you are saying that 100% of fast neutron energy is. Oh no, it's no. I don't assume 100% of fast electron energy is used to ionize helium. This is okay. Okay. Oh, probably this was misleading somehow. Oh no, it's not misleading. So okay. When I calculate this work per ion pair, I use some abundance pattern, and so in the sense that we assume like 1% of helium, and then how much energy goes to this 1% of the helium. That's no, I'm sorry. Oh, let me see. So okay, so this is the ionization rate per ion. So energy deposition per ion times the helium number density. So it should be this is the ionization rate per unit volume per second per helium. That's the ionization rate here. So I'm not assuming the whole energy is going to the helium. Did I answer your question? Yeah. Yeah, I take into account this fraction of helium fraction, not just yeah. Yeah.
Have a follow-up? Yeah.
Okay. So right. So can I continue or?
Yeah, it's up to you if you think there are further clarifications on Q dot.
Yeah, Q dot is the
okay.
heating rate per ion. Yeah. That's,
okay. Yeah. Then keep on.
yeah.
Keep on
Okay.
going, and we can follow up. I encourage people also to use the Slack of the meeting. So yeah, go ahead.
Okay, so when magnet forms, so this was the question related to the Woody's question, but I repeat, this is work done by my colleagues. And if there is a stable neutron star remnant exists, and then it releases rotational energy, push the ejector, you will have faster and energetic ejector than the normal ejector. So in that case, the kilonova actually, you don't really change the luminosity so much, because the energy is kind of determined by the total mass, not the total kinetic energy. But you get the much redder emission because it's faster, so that it's cooler. But the radio emission is really bright. Even if you take like 10 to the minus 3 per cubic centimeter, you will have crazily bright signal. So that's what Udi said. It should be observed in even the radio blind survey. That's kind of interesting. And also this is not crazy to think about the fraction. Think about this kind of transients, because fraction of such low mass major events are not so, shouldn't be low, so that we may be able to see this phenomena in O4.
Can I ask a question?
Yes.
So just to understand, I mean, the point here is that as long as you pump in energy before the ejector becomes optically thin, you know, this energy going going to push it. So actually, what matters is that the spin down will be shorter than the time it takes to ejector to reach the radius at which it's optically thin. So it doesn't
Right.
really have to be a magnetar. I mean, even
Oh, yeah.
if my numbers are correct, you know, even at a
Okay.
field of
I
10 to
would say it's
13 Gauss,
pulsar.
and
Yeah.
so the parameter here, which is important, is the rotation speed. It's if you have a millisecond, you know, pulsar with 10 to the 13 Gauss, I think that the spin down will be still shorter than. I'm not completely sure about. It depends on the velocity and mass of the ejector, but for supernovae,
Okay.
you know, in
Yes,
collapsar,
I agree
it's
with you.
even.
Yes, I agree with you. It's not necessarily magnetar. So I believe I didn't put magnetar in this slide, but anyway. So yeah, it's pulsar. Pulsar like, and we know what the rotation and what the mass of the star, so that.
So it's quite robust argument. I mean, basically, you are saying that there is a.
Can I make a comment?
Yeah.
Following Udi's remarks, I made some simple estimate that if there is even a small asymmetry in the neutron star, then the energy may be lost by gravitational waves. And,
That's true, yeah.
And then this solves the problem very neatly, because these gravitational waves are too weak to be detected on one hand, at least with current detectors. But they won't influence, of course, either the kilonova or the radio. And I think that this suggests that we should look in the simulation for the level of asymmetry in the neutron star, which is formed.
So actually, it's been done. There are papers on this, and the conclusion is that you need a magnetic field larger than 5 times 10 to the 16 Gauss to produce a deformation, which is, you know, which is high enough to.
The magnetic field is not the only way to produce a deformation. It may be born deformed, and then may stay deformed. The merger is not axisymmetric. There is the point in which the stars collided, and this may induce some non-spherical structure that even possibly deep in the interior. And this is something that we have to look for in the numerical simulation. I mean, to me, one of the lessons of this exercise is that you have to look for built-in deviation from symmetry. And a small one, 10 to the minus 2, 10 to the minus 3, may dominate any magnetic field emission.
I mean, 10 to the minus 2 is a huge one, right?
Yes, yeah, I agree with Philip. But I don't know. It's so numerical relativity simulation can see, you know, the non-axisymmetric radiation after, you know, after a few tenths of milliseconds. But there must be some limit if the, you know, this deformation is so small, it can't be resolved. But yes, it's possible to radiate the rotational energy to gravitational energy. Yeah. Any comments
think that
from?
This is the only way out of this conundrum.
Sorry.
I think that this is the only resolution to this puzzle that will be posed.
Mm-hmm. Okay, yeah, good. So any comments from simulation side on this small deformation can survive like 100 seconds, 1,000 seconds, and then continuously radiate rotational energy to gravitational energy?
We have the hand raised from David Radice. Yeah, and you, Kenta, want to make a comment as well? Let's yeah, first go ahead, David, who raised the hand. David, do you hear me? I don't know if something else wrong on my end. Sorry.
No, it might be muted. Is it
Ah.
muted?
No.
We don't hear. Okay.
Okay, Kenta.
Okay, I have
Yeah,
intro.
go ahead.
Okay. Sorry, David. Okay, so this is the magnetar. Sorry, pulsar thing. So the next thing is what we can from nebula phase. So in the first argument of the energy conservation, I said the first peak only element. We can't explain the heating rate. That's coming from this observation. So this is Spitzer telescope observation at 43 days and 70 days after the merger. And then, unfortunately, for GW17 for Kilonova, the Spitzer was the only telescope it could see the Kilonova because it was too close to the sun that other ground telescopes couldn't see. But anyway, the Spitzer telescope detected this. So this is the host galaxy here, and this is the location of the merger. At 4.5 micron, the telescope really saw the emission, and it's gone after 200 days. So the interesting thing was there were detection at 4.5 micron, but only the upper limits at 3.6 micron in both epochs. So this already tells us that the spectrum of nebula phase is quite interesting. So there must be some strong line emitters. It's not must be, maybe this suggests that there is a strong line emitter around 4.5 micron. And what is this? So Kilonova modeling size, we have been struggled to figure out what really this 4.5 micron means. And we have sort of investigated this. So this is the, first of all, so what is 4.5 micron energy scale means? So 4.5 micron means it's less than electron volt scale. And this is actually for heavy elements, this is energy scale of fine structure, which means, just fine structure splitting of the ground state the transition between these fine structure split levels can emit 4.5 micron radiation. And actually, we found that these fine structure lines are really effectively carried away the radioactive heat. And then it can be significant fraction of the radioactive heat carried away by the M1 transition. So what we have to do is to construct the line list of forbidden lines or fine structure lines for all the elements. But if you try to do this, you will encounter this problem. So if you go to the database and try to search the forbidden lines or M1 lines, or in other words, fine structure lines, you got just error message that no lines are available and with these parameters. But what we can do is, even though there are no lines, there are levels. So those are experimentally calibrated levels of tungsten, so doubly ionized tungsten. And then we know what's the configuration, what is the term, what is the total angular momentum. And then uncertainty is quite good. It's good enough to create Kilonova's nebula spectrum. So with this given energy levels, we could use the selection rule to construct a line list. So we go over all the experimental data and then create, based on the energy level identification, we construct the M1 line list using selection rules. And then this is the ions that covered by this our line list, which constructed in this way. So it's up to include, this line list includes up to Einsteinium, its atomic number of 99. So we have now, there are some missing atoms that are because of these missing energy levels that are experimentally calculated. So, but I would say we have good coverage of the elements. Those are experimentally calculated. And then we can compare this experimentally calculated line list with the observed data. This is one example. So for example, if you take the ejecta composition, which is dominated by the first peak elements, then you get this kind of spectrum. So here is the Spitzer upper limit, and here is Spitzer detection, 4.5 micron. So the spectrum is look like this, and then emission is completely dominated by a single element, which is selenium. And on the other hand, if you don't have first peak, you can still explain the data with the tungsten. So this is the maybe quite interesting that maybe Spitzer telescope did see emission lines from tungsten and osmium. Those are in the third peak, but we can't really conclude with just one upper limit and one detection. Anyway, but after JWS, James Webb will be starting the observation, and then we have, once we have neutron star merger close enough to take JWST spectrum, then we can do like this. So this is the nebula spectrum in full wavelengths, like from 0.5 micron to 40 micron. And probably James Webb will be able to see this kind of structures, and then hopefully we can start to argue that's what elements are really formed from these emission lines. Okay, so, and of course, this is nebula phase, so where I'm talking about the time scale of few weeks to months and year time scale, that's the nebula emission. But of course, there are some interesting arguments. Maybe we can look for kilonova remnants. So it's like supernova remnants. And this is, for example, gamma ray emission from kilonova remnants at 100 kilo year at 3 kiloparsec. So these are all emitted from radioactivity, and we may be able to search this kind of nuclear gamma rays from kilonova remnants. But of course, another question is, this is open question, that how about emission of the other wavelengths on the various timescales, how kilonova remnants look like? That's, I would say, it's completely open question. Okay, now I'm entering some technical questions. So first thing I would like to discuss is how good are atomic data? So here I'm showing selected lines which have large enough oscillator strengths, and then they might play important role in the spectrum formation. So, for example, these are Singlian zircon and lanthanum and cerium and strontium here. So these lines are completely coming from atomic code. So we don't use any experimental data. And then maybe you can recognize that in a few minutes ago, I said strontium line, there is a strong strontium line at 10,000 angstrom. But as you can see here, the strontium 2 lines are not around 10,000 angstrom, but it's even 20,000 angstrom. That's because atomic code is not perfect. So you have to really calibrate what atomic code says with experimental data. So once you use, for example, experimentally calibrated energy levels, you can shift, those lines are shift. So this is done by this PhD student, Domoto-san. So she ran atomic code and then selected strong lines, and then go to the database and then try to calibrate all the recalculate wavelengths of each lines. So this is quite tough work, but they managed to do it. So now the wavelengths are corrected. However, of course, you can see the problem that even though you can correct the wavelengths, we can't be sure that oscillator strengths are also oscillator strengths may change as well, but we cannot really correct those. We don't have good way to correct oscillator strengths, so that what we can do is just to trust oscillator strengths from the atomic code and then change the wavelengths to the correct wavelengths. So that's what we can do currently. But if you accept this method, we can start to say, for example, the other spectral feature seen in a spectrum. For example, this here is a strontium-2 signature. This is observed, and this is synthetic spectrum. And then this is strontium-2 line, and you can see strontium-2 line around the correct wavelengths. And at the same time, you can see some structure around here, which is lanthan-3 and then cerium-3. So probably those are what we see is maybe cerium and the lanthan. So, but we need probably better spectrum from the space to really conclude robustly. Okay, so maybe I run out of time. Maybe the next question is quite technical about non-LTE, so maybe I should stop here, and then I'm happy to take questions and comments.
Yeah, let's give people the chance to ask questions. I want to come back to David. Are you still around? Do you want to try again about the inhomogeneous is David, do you hear me? David Radice?
Maybe he has some still.
Yeah, okay. Okay, let's then give the opportunity to others. Okay, yeah, his mic is not working.
But he can probably write the chat on the chat if he wished the question. I mean, we can.
I think we were discussing about how inhomogeneous the numerical relativity post-merger can be. I think.
How homogeneous? Wait, is this in the chat?
No, I think that he was trying to answer. Okay.
Oh yeah, elliptical.
Yeah, it was related to three questions.
Yes.
Okay, thanks, David. And then
yeah,
we have
that's
a comment from Carlo on the chat.
Okay, R mode, yes.
Mm-hmm.
But probably the question is, R modes are efficient enough to R modes are efficient enough to release the rotational energy. Okay, time scale of order of seconds. Okay. Okay, so probably R mode emits all the.
Right. Yeah. Very interesting.
But does it depend on the magnetic field? If you have very strong magnetic field, does it R modes may be suppressed, or do you have any idea on that?
So can you hear me?
Mm-hmm. Yes.
Yeah, so just a very brief comment on this. Yeah, in fact, R mode, I mean, this is, I think, the results that I was mentioning about their instabilities are actually perturbative. So I don't think there's simulations that can extend, I mean, in full general relativity, that can extend long enough to see their growth. But they were several years ago proposed as a possible mechanism for spin down of rapidly rotating hot pulsars. So
Okay, thanks.
Okay, are there more questions or comments?
So may I say comment about the post-merger evolution? So sorry, I'm just
Sure, yeah.
Yeah, post-merger evolution is as David said that it's a highly unclear. So because in the presence of so neutron cooling and the magnetic field, so we could have a turbulence and the dynamo and the Taylor instability and something like this. And then so naive estimation shows that the time scale for instability is about second to 10 seconds. So then but it's not possible to do a exact analysis for this. So yeah, turbulence and dynamo and the Taylor instability and so on. Then so it's not very clear. Anyway, so yeah, physics is highly complicated. This is my comment.
Yeah, and also maybe I should say that in your work and Kawaguchi and Fujibayashi, that differential rotational energy will be released really rapidly, right? Within few seconds, 1 second. It's even this energy is quite large.
Yeah, so also it's this time scale depends on the process of turbulence and the dynamo and something like this. So it's not very clear. Our calculation based on very simple assumptions. So
Okay.
Okay, thank you, Masaru. More comments?
Maybe just a question. Going back to this idea by Tzvi of gravitational waves, if I'm not mistaken, the gravitational wave power scale is the rotation speed to the 6th power. It's very sensitive. So, even if you just reduce the rotation speed by a factor of 2, you will actually, now it depends on the strength of the magnetic field, but so the question if, it's enough to reduce because the energy, the rotational energy scale is the omega squared. So, question if it's would be enough to kill enough energy.
This calculations that goes to the Crab pulsar, which we know when it was born. And if you take the slowdown just in magnetic field, you get the life. You get it a factor of about 2 in the estimated lifetime. So I mean, you cannot get to the. Sorry, it's the other way around. It must have been born either it was born very slowly, not much faster than the current velocity, or something else happened. And long before all these arguments, it was suggested that the dominant energy that it was born fast, and the dominant energy that was released by gravitational waves. This is even in Shapiro and Tucholsky in the classical book.
But the Crab has a field of 10 to the 12 Gauss. If you go to a magnetar, I mean, that's why I'm saying it sets an upper limit on the allowed magnetic field, I guess, right?
Can I have also comment about the magnetars? This is Udi. In a bit different direction. First, some use the fact that in GW 170817, the ejecta energy was about 10 to the 51 ergs to argue that the central remnant should collapse quickly. So the magnetar will not inject energy into the ejecta. Given what we discussed, it's probably not a good argument. So now we are talking about how 10 different ways to kill the magnetar energy injection or the rotation and energy injection. So I also did use this argument. I don't think we can use it anymore. And
That's
second,
right.
it's I don't know if it's ironic, but often we invoke our magnetar whenever we want. So whenever there is some observation that we cannot explain, we invoke magnetar, and this magnetar solves everything we need. It's not clear at all that that magnetars are really sources of this amount of energy in nature. I think that we forget that. So we know that there are magnetars which are rotating slowly. We don't know what was the rotation when they were born. We always assume that if a neutron star is born rotating fast enough, it will be a magnetar, and then we can have its energy to do whatever we need to explain the observations. But given, if indeed we will be, and this is something that I guess hopefully we'll see in 04, if we'll see that low mass binaries merge and this energy is not released, then we at least will know that this is not a viable engine. And I think we sometimes forget that. Everybody is considering magnetars as something which is extremely solid as an energy source. I'm not sure. We don't have even a single observation that requires a magnetar injecting energy.
But that wasn't your point. I mean, in core collapse, you're right. We don't know what's the rotation speed, and now it seems not a problem to produce 10 milliseconds.
No, it's not my point. It's not my point. It's a point about another thing, not about this.
But I thought you said that in binary mergers, you know what is, from the angular momentum, you can estimate what is the rotation speed of the born neutron star.
Yes. What I was saying is the following. Now we've just made a lot of discussion explaining why a fast rotating neutron star may not be radiating its energy into the outflow. Okay. Not only that, there are some observational indications that when such a rapid neutron star is born or after a merger, we have these conditions. Somehow this energy is not finding its way into the ejector. This is one thing. The other thing is that whenever we see something that doesn't fit our model of nickel or whatever, we say, oh, it must be a magnetar. That's it. This is all I said.
Oh, okay. I mean, you want to argue that based on this,
based on this and based on all other.
Okay.
I cannot say that we can rule out. I just said that we are not even sure that magnetars or fast rotating neutron stars exist. We never saw one. So no, maybe we should be more careful when using them.
What's the okay, right.
That's it. That's all I said.
Yeah, I agree. We may be able to say more in 04. It's just right. Low mass neutron star merger shouldn't be so rare, so that we may be able to say in the next year.
I think that it's you mentioned it, but I need to stress it again that in all short GRBs for which there was radio observations, there were upper limits on magnetar activity, radio observed from the radio, and these upper limits were quite significant. You can almost rule out 10 to the 52 magnetars with energy injection with certainty.
Yes, so this suggests to me that either magnetar cannot do anything, or the merger channel forms magnetar cannot make short GRB. Yeah. Okay, so everybody is interested in the magnetars, but any more comments, questions?
But Kenta, I wanted to hear your opinion because you indicated some uncertainties about opacities and lines. What do you think about the remarks that I've heard, that we have heard in another meeting, stating that that the atomic data is so poor that we practically won't be able to calculate robust Kilonova light curves?
Okay, so you are asking a difficult question. Right, so what I'm thinking is, so first, okay, theorists have to answer that how hopeless is it? And let's take, so as I said, different atomic data will give us sort of inaccurate wavelengths, and the oscillator strengths also may be quite a bit off. But for example, what we can do is take different codes, different atomic codes, and then to gather it and then run simulations, and how outcome would be different. And if the outcome is, so theorists usually claim that there are so many lines that statistically smeared out, so light curve shouldn't be so dependent on the exact atomic data. But we should confirm it. And we should take different atomic data and then try to run, and if the what outcome would be independent of the atomic data or atomic code. So those tests should be done. And also, I'm not that pessimistic because the spectrum is quite beautiful. I mean, so if spectrum is so complicated, maybe it's very difficult, but spectrum look like quite beautiful black body. There must be some beautiful physics working. So at least at this point of view, we should be able to extract robust information from the spectrum or light curve. That's I'm not that pessimistic. But we have to do many, tests that justification, so on and so forth.
Okay. Thank you very much, Kenta, and thank you for all the comments. We're already past time. So yeah, thank you very much again, Kenta, for this great discussion, for this great